Hi everyone, I am SANTHI from Department of Mathematics and Statistics, Bhavan's Vivekananda College. I am here with my lesson 33 from linear algebra on eigenvalues, eigenvectors and diagonalization. In this lesson, I am going to explain about complex eigenvalues of a matrix. Let us learn now the concept complex eigenvalues. Let A be an n by n matrix. The characteristic equation of A is that A minus lambda I is equal to 0. This is as usual what we have done for real eigenvalues before. Then if for each value lambda in C, that is C is here field of complex numbers, there exists a non-zero vector x in Cn, that means column vector in Cn, that means Cn will have all n rows column vectors, where each entry is a complex number such that Ax is equal to lambda x. Then we call lambda a complex eigenvalue and x a complex eigenvector of A corresponding to lambda. And here we have to remember a point that here it is not that the matrix A be having complex numbers as entries. Matrix may be having real numbers as entries, like you may have a matrix with like 1 1 something 2 3 some numbers which are real numbers only. But if you try to solve its determinant, that A minus lambda I, and try to find the eigenvalues, if you get complex numbers as eigenvalues, then those eigenvalues we call them as complex eigenvalues, and the corresponding eigenvectors we call them as complex eigenvectors. So this is what complex eigenvalues we mean by complex eigenvalues. Now in this concept we particularly concentrate on 2 by 2 matrices only. So in this regard I just want to give you a few more points about this complex eigenvalue. So note, there is a note which you have to note it down. So if you have consider a matrix, first point under note, a matrix A, consider a matrix A. If lambda is an eigen, I can say not only just eigen, lambda is a complex eigenvalue of matrix A, then its conjugate lambda bar is also an eigenvalue of A. So that is like, I can show one example. Suppose if 2 minus I, lambda is equal to 2 minus I is an eigenvalue of A, then I can say lambda, what is the conjugate of lambda bar? What will be that? It is 2 plus I is also an eigenvalue of A. That is, anytime, even for equations, complex numbers always exist in pair. A complex number and its conjugate as a solution. This is point number 1. And then point number 2, or I can say this, even I can generalize this. That is, so generalizing the same above fact, I will write if lambda is equal to A plus IB is an eigenvalue then lambda bar is equal to A minus IB. This is also B. A minus IB is also an eigenvalue of A. This is the point number 1, and let us see the point number 2 in this. Point number 2 is, this is regarding eigenvalue. Then let us see the eigenvector the same way. If V is an eigenvector of lambda, then V bar, that is conjugate of V, is an eigenvector of lambda bar. So this also we can give an example. As an example, if V is equal to, suppose I have like this, I plus 1 and then 2 is eigenvector of lambda. For lambda, if it is eigenvector, then how do you write V bar? V bar means you have to take in this conjugate of I plus 1. How do you write conjugate? Wherever the imaginary number is there, you have to take minus I plus 1. Then for 2, 2 is itself is conjugate. For any real number, the same number itself is conjugate. So, is eigenvector of lambda bar. So, these two are the main points you can remember. Now, let us work out a problem in this concept. So, find out. So, question number 1. Find the eigenvalues and a basis for each eigenspace in C2 for the following matrix. So the matrix is given. A is equal to 5, 1, minus 8, 1. So the solving this problem is as usual the same procedure what we do for the real eigenvalues. So here A is given. A is equal to 5, 1, minus 8, 1. So what is the characteristic equation of A then? So characteristic equation of A is that A minus lambda I is equal to 0. So that implies that 5 minus lambda 1 minus 8 1 minus lambda is equal to 0, which implies 5 minus lambda into 1 minus lambda, then plus 8 is equal to 0. So 5 minus 5 lambda minus lambda plus lambda square plus 8 is equal to 0. So this is lambda square minus 6 lambda plus 13 is equal to 0. This cannot be split because 13 is a prime number. So if you find its a discriminant delta b square minus 4ac, that is 36 minus 452, so which is less than 0. So it will have imaginary values, imaginary solutions, no real solutions for this, or complex solutions you can say, not real solutions. So let us try it with x is equal to lambda is equal to minus b plus or minus 6 plus or minus under root of b square minus 4ac by 2a. So it is, this is equal to 6 plus or minus under root of minus 16 by 2. So this is 6 plus or minus 4 root minus 1 by 2, that is 6 plus or minus 4i by 2 is equal to 3 plus or minus 2i. So lambda is equal to implies I have, what are the eigenvalues we have here, implies lambda is equal to 3 plus 2i and lambda is equal to 3 minus 2i are eigenvalues. So we can observe here the two, one is it is lambda bar, you can say lambda bar is 3 minus 2i. So two eigenvalues are conjugate to each other. Now we have to find the eigenvectors. So eigenvectors for lambda is equal to 3 plus 2i. So this is consider, what do you have to consider for this? Consider det A minus lambda I for lambda is equal to 3 plus 2i. What it is? So it is det A minus 3 plus 2i I, that is equal to determinant of, you will have 5 minus lambda 1 minus 8 1 minus lambda, and here this is equal to that 5 minus 3 plus 2i 1 minus 8 1 minus of 3 plus 2i, that is equal to, so 5 minus 3 2 minus 2i and 1 minus 8 and a minus 2 minus 2i, this is 1. Now we have to consider the augmented matrix. Now consider let us take consider x is x, or let us call it as v is equal to v1 v2 be eigenvector. Then we have that A minus lambda I, this one not that, A minus lambda I into V is equal to 0. So to solve this, so consider augmented matrix. Augmented matrix. What is that augmented matrix? A minus lambda I with 0. So that is equal to 2 minus 2i 1 0 and then minus 8 minus 2 minus 2i 0, that is equal to, if you you try to here this, if you observe, you cannot try to apply any transformations. So what do I do is consider I'll multiply this and I'll try to solve the equations, because only 2 by 2 matrix and applying the transformations for this will be very difficult. So what do you do is here, this you will multiply directly with v1 v2 is equal to 0 0, then you will get the equations 2 minus 2i into v1 plus v2 is equal to 0 and minus 8 v1 plus minus 2 minus 2i into v2 is equal to 0. This is equation 1 and equation 2. Now we need to solve these two equations. So what do I do here is, I'll try to eliminate the first v1. So multiply the first equation with 8 and then add second equation, multiply with 2 minus 2i. So what do we get here? Multiply the first equation with 8, 8 into 2 minus 2i v1 plus 8 v2 is equal to 0. And the second equation, multiply with 2 minus 2i, then it will be minus 2 minus 2i into 2 minus 2i v2, then this will be equal to 0. Then add these two. So this This implies you have this 8v2 and then plus this. I will write it as, if you take a minus common, so it is 2 plus 2i into 2 minus 2i into v2 is equal to 0. That implies 8v2 plus minus, and this is a plus b into a minus b, so it is v2 is equal to 0. That implies 8v2 plus minus 4 and then plus 4, this is into v2 is equal to 0. So it is 8v2 minus 8v2 is 0. That implies 0 is equal to 0. So what do you mean by this? That implies equation 1 and 2 represent the same. So you need not solve in these two 2 by 2 for 2 by 2 matrices. If you get like this, it means these two represent the same equations. So any one equation you can take, either first equation or two, a second equation, either first equation or second equation, and you can write the eigen vector. So I will consider equation 1. Consider equation 1. So from equation 1, or let us take equation 2. Then what you have in equation 2 is minus 8v1 plus minus 2 minus 2i v2 is equal to 0. That implies I can say minus 8v1 is equal to, so it is minus of minus 2 minus 2i into v2. So this implies v1 is equal to minus 2 minus 2i by minus 2 minus 2i by 8 into v2. So take minus 2, if you take it common, so you'll get 1 plus I by 8 v2. That implies v1 is equal to minus of 1 plus I by 4 v2. So what can I write? The vector, characteristic vector, what I got, v is, therefore characteristic vector v is equal to, v1 is v1, we thought it as v1 v2, so v1 v2, then what is v1? v1 is minus of 1 plus I by 4, and then this is v2, 4v2, and this is v2. So this I can write it as v2 if you take it common, v2, and also if I take 4 also as common. So whatever, how much ever maximum possibility you can take. So it is minus of 1 plus I, and then this will be, we are multiplying with 4, so it is 4 by 4. That implies v, we can consider it as minus 1 minus I 4. This is one eigenvector. Now for this is eigenvector for lambda is equal to 3 plus 2i. Now we don't need to find separately for lambda is equal to, lambda bar is equal to 3 minus 2i. We have written that point that for lambda bar is equal to 3 minus 2i, eigenvector will be conjugate of v, that is v bar. So what will be that conjugate vector? How do you write conjugate vector? For v, the conjugate vector is whatever here you have, minus 1 minus I. So conjugate of minus 1 minus I, conjugate is minus 1 plus I. So it is minus 1 plus I, and conjugate for 4 is 4 itself. So it is 4 is another eigenvector. This is how to find eigenvalues and eigenvectors, complex eigenvalues and the corresponding eigenvectors. So now the basis for eigenspaces, basis for eigenspaces for lambda is equal to 3 plus 2i, v is equal to minus 1 minus I4 eigenspace for E lambda is equal to set containing V. It is very simple. It is nothing but minus 1 minus I for set containing the vector. And similarly, for lambda is equal to 3 minus 2i, we have eigenspace lambda bar. This is E lambda bar is equal to V bar, which is equal to set containing the vector minus 1 plus I4. This is what the finding the eigenspace also. Now we will do one more practice problems. Now we'll go through a result on complex eigenvalues of a 2 by 2 matrix. So let A be a real 2 by 2 matrix with a complex eigenvalue, that is in the form of lambda is equal to A minus bi. This is this format you have to remember. B not equal to 0, and V is its corresponding eigenvector in C2. Then we have A is equal to PCP inverse, where what is P here? P is a matrix which is in the form of, this is a form, its first column is real part of V and the second column is imaginary part of V. So real part of real, this means real part in V, and this means imaginary part in V. That means suppose I have here V is equal to, suppose we have 2 minus 2i and 2. Then what will be real part of V? In this real part is 2 and this 2. This is a column vector. And imaginary part of V is, in this the imaginary part here is, in this it is minus 2, and then here imaginary part is 0. So this is matrix P, and then C is a matrix which has the values A minus B, B, A, where A and B are taken from the eigenvalue lambda. So using this result, now let us work out a problem using this result. So based on this result, let us work out a problem. Find eigenvalues and a basis for each eigenvector in C2 for the following, and also find an invertible matrix P and a matrix C such that A is equal to PCP inverse and the matrix A is given as 1 minus 2, 1, 3. So let us go to its solution. So here A is given as 1 minus 2, 1, 3. So let us write its characteristic equation. That A minus lambda I is equal to 0. Solving, it is 1 minus lambda minus 2, 1, 3 minus lambda is equal to 0, which implies 1 minus lambda into 3 minus lambda plus 2 is equal to 0. That is 3 minus lambda minus 3 lambda plus lambda square plus 2 is equal to 0, which implies I have lambda square minus 4 lambda plus 5 is equal to 0, which cannot be split, and implies lambda is equal to minus b plus or minus b square minus 4ac by 2a. So it is 4 plus or minus under root of So this is minus 4 by 2, which will be equal to 4 plus or minus 2i by 2. It is 2 plus or minus I. So therefore we have lambda is equal to 2 plus I, lambda bar is equal to 2 minus I are the eigenvalues. And then what will be, we have to find the eigenvectors. To find eigenvector for lambda is equal to 2 plus I. So for this, what do we do? Consider. So directly we'll write let V is equal to V1, V2 be eigenvector, implies we have A minus lambda I into V is equal to 0. That implies, so what is A minus lambda I? We have A as it is 1 and minus lambda is 2 plus I and then minus 2 and then 1, 3 minus of 2 plus I into V1, V2 is equal to 0, 0. So this will give us the equations. It is 1 minus 1 and then minus I and minus 2, 1 and then 1 minus I into V1, V2 is equal to 0, 0. Which implies we'll have the equations minus 1 minus I into V1 and then minus 2 V2 is equal to 0 and 1 into V1, that is, I can see it is V1. So V1 and plus 1 minus I into V2 is equal to 0. This is equation 1 and then equation 2, and we have observed. So I will consider 2 implies we have V1 is equal to minus of 1 minus I V2. Therefore, what is eigenvector V is equal to V1 V2, which is equal to minus of 1 minus I V2 and then V2, that is equal to V2 into minus 1 plus I and then 1. Hence, eigenvector for lambda is equal to 2 plus I is V is equal to minus 1 plus I 1. Then what will be the other eigenvector? And then the eigenvector for lambda bar is equal to 2 minus I is the conjugate of V. That is, V bar is equal to, how to write conjugate of V in the in V, in place of like for the imaginary you have to change the sign. So it is minus 1 minus I and then for 1 it is 1 itself. So this is V bar is equal to, this is the other eigenvector. So the two eigenvectors we have like this now. For lambda is 2 plus I, V is equal to minus 1 plus I1, and for lambda bar is equal to 2 minus I, we have V bar is equal to minus 1 minus I1. Then what is eigen space here? Basis for eigen space. Basis for eigen space for E lambda, it is equal to set containing minus 1 plus I and 1, and for E lambda bar it is So this one is E lambda bar, it is equal to minus 1 minus I 1. Now we have to get P and C matrices. So our next aim is to find matrices P and C such that A is equal to PC P inverse. So for A is equal to PC P inverse, now we have to find P and C. So for this, what do we have to take? We have to consider either lambda or lambda bar. I am taking for lambda is A minus BI. Let me take it as 2 plus I, which implies I have A value is 2 and B value is minus 1. Then what is that? We have the point, we have P is equal to it is a real part of V and imaginary part of V. Now what is V for lambda is equal to 2 plus I? For lambda is equal to 2 plus I, the eigenvector V is minus 1 plus I and 1, right? Minus 1 plus I, and so what is the real part in this? In this real part is minus 1, 1, and the imaginary part is equal to 1 and then 0. So P will be the matrix minus 1, 1 and then 1, 0. And then what is the next one? We have to get the matrix C. C is equal to, what is the formula for C is A minus B, B, A. So A minus B, B and then A. Then if you take like this, you can check here. A is equal to PC P inverse such that A is equal to PC P inverse. So to check this, you can even check AP is equal to P into C. That you can consider and you can confirm with this. So let us check for that. AP is equal to CP. So what is AP? What is the matrix A here? 1 minus 2, 1, 3. And what is that P matrix we got here? The P matrix is minus 1, 1, 1, 0. So minus 1, 1, 1, 0. With the product is minus 1, minus 2 is minus 3. And then 1 plus 0 is 0. Minus 1 plus 3 is 2. And then 1. And then what is P into C? P is minus 1, 1, 1, 0 into C is 2, 1, minus 1, 2. And the product is here minus 2, minus 1 is minus 3. And then minus 1 and then plus 2 is equal to, minus 2 plus 2 is 0. And next one is 2 and then minus 0, 2 plus 0 is 0 and 1 plus 0 is 1. So these two are equal. It is verified.